ratio of the number of turns.
It is the simplest, most reliable, and arguably the most vital machine on the power grid. The transformer is the master that makes long-distance electricity transmission possible. Its entire existence rests upon a fundamental principle: the flawless ability to efficiently change alternating current AC voltage, the very core function of this device. Zero. The heart of the transformer is simple. Two coils of wire, the primary and secondary, that communicate purely through magnetism, never touching. The primary winding is where the AC power first enters the system. This initial voltage sets up the entire electromagnetic conversion cycle within the transformer. When AC flows through the primary coil, it generates a constantly changing magnetic field. This dynamic field is the true working medium of the transformer. Crucially, because AC continuously reverses, the magnetic field it creates also continuously reverses polarity. This constant reversal is what the transformer relies on for efficiency. This changing magnetic field is then guided by the core. Made of laminated steel, the core acts as a perfect pathway, ensuring maximum efficiency of the magnetic transfer within the transformer. The laminated sheets prevent eddy currents and wanted circular currents that would otherwise waste energy as heat within the core. This design maintains the transformer's incredible efficiency. The magnetic flux, perfectly contained by the core, then reaches the secondary winding. This link is where the transformation of voltage physically takes place. According to Faraday's law of induction, a changing magnetic field induces a voltage. The core delivers this changing field directly to the secondary coil, creating a new voltage. The fundamental relationship is the turns ratio. The voltage produced is directly proportional to the number of turns in the secondary coil, dictating the transformer's output. For a step-up transformer, the secondary coil has significantly more turns than the primary. The transformer deliberately increases the voltage for efficient transmission. Step-down transformer. The opposite is true. The transformer lowers the voltage, making the power safe and usable for homes and local businesses. This entire relationship maintains power conservation. The transformer ensures that if the voltage goes up, the current must precisely go down. The transformer's ability to step up voltage is the single key to the modern power grid. High voltage dramatically lowers the current needed for long-distance transmission. The transformer assembly is often submerged in oil, not for lubrication, but for insulation and cooling, managing the intense heat generated during its operation. This cooling system uses convection. The oil near the hot core rises, cools, and returns. This constant thermal cycle protects the core and coils of the transformer. Beyond the main windings, a transformer contains safety features. A breather is used to keep the vital internal oil moisture-free and clean. Buckhole's relay is another vital protection device. It monitors the oil and gas buildup caused by internal faults within the transformer, providing an essential warning system. Safety and grounding. The transformer tank is connected to the earth. This prevents dangerous voltage from building up on the outer casing. The lifespan of the transformer is largely dependent on the health of its insulation and oil. Regular testing is performed to check the oil's dielectric strength. In distribution substations, tap changers allow personnel to manually adjust the number of active turns in the coil, fine-tuning the output voltage of the transformer. For large power plants, on-load tap changers OLTC automatically make these adjustments while the transformer is running, maintaining perfect voltage stability for the grid. Though mostly seen as large industrial units, the same transformation principle applies to miniature ferrite core transformers used in small electronic circuits. These small versions, often hidden in your chargers, perform the final step, reducing voltage to the precise level needed by your phone. A tiny, but vital transformer. The transformer's dependence on changing magnetic flux is why it cannot work on DC direct current, which maintains a static magnetic field. If DC were applied, the primary coil would simply act as a short circuit, potentially destroying the winding without generating any output voltage in the secondary of the transformer. The concept of mutual induction is therefore exclusively tied to the dynamic nature of alternating current, making the two systems fundamentally inseparable. From the point of generation to the final point of consumption, transformers handle the voltage needs at every single stage of the power grid. This mastery over voltage is the core reason why the vision of a C, championed by Nikola Tesla, ultimately became the global standard over Edison's DC. The engineering of the transformer, with its reliance on precise coiling and efficient magnetic guidance, allows humanity to harness electricity across vast distances. The transformer is not just a component. It is the silent, efficient backbone that delivers power to billions across the planet. If you enjoyed this deep dive into the magnetic mastery of the transformer, please let us know in the comments below. Like, share, and subscribe to UA Electric for more essential engineering explanations.